So this time we're taking a look at section 11.8, which deals with power series. So we're going to start out with the definition of a power series. So a power series is a series of the form the summation n equals 0 to infinity of c sub n times x to the n. Now if you think about what the terms are going to look like, if you have n equals 0, you'll have c sub 0 times x to the 0. Well, that's just going to give us c sub 0. And then with n equals 1, we'll have c sub 1 times x to the first. N equals 2, we'll have c sub 2 times x to the second. And so forth. Now, one thing to keep in mind is that power series may converge for some values of x and not for others. Alright, but you can be a little bit more general with this. So, more generally, we can talk about a series of the following form. So we might have summation n equals 0 to infinity of c sub n times x minus a raised to the n. Now, if n is equal to 0, you'll have c sub 0 times x minus a to the 0. That'll just be c sub 0. Then when n is 1, you'll have c sub 1 times x minus a raised to the first. Well, that'll be c sub 1 times x minus a. And if you have n equals 2, you'll have c sub 2 times x minus a raised to the second. So if you have a series of this form, this is called power series in x minus a, or a power series centered at a. So I'm going to show you some examples in which we consider some power series, and we're going to figure out the x values for which these power series converge. All right, so let's take a look at the first example here. And in this example, we'll ask for which value of x is the series, and this one is going to be summation n equals 0 to infinity n factorial times x to the n. So for which values of x is that given series convergent? Now, to answer this question, we're going to be taking a look at the ratio test. so once again, we're going to be using the ratio test, and if we're going to use the ratio test, then we need to know something about a sub n, and we need to know something about a sub n plus 1. So our a sub n is n factorial times x to the n, and our a sub n plus 1 is n plus 1 factorial times x to the n plus 1. So let's take a look at the limit as n approaches infinity. Absolute value of a sub n plus 1 over a sub n. Now, we're really going to be somewhat fortunate with how this works out, because when we take a look at the absolute value a sub n plus 1 over a sub n, well, the a sub n plus 1 gives us n plus 1 factorial times x to the n plus 1. And then the a sub n gives us n factorial times x to the n. Now remember from the previous section, we were dealing a bit with factorials. Actually, previous couple of sections we were taking a look at some factorials. And you may recall that n plus 1 factorial is the same as n factorial times n plus 1. So if I divide the n plus 1 factorial by n factorial, what's going to remain is the n plus 1 here. And so we're going to get, this is the limit as n approaches infinity. Absolute value of n plus 1 times, well, x to the n plus 1 over x to the n gives us x. And so as n gets larger and larger, we know n plus 1 is going to be positive. But here's the thing. This limit as n goes to infinity, absolute value of n plus 1 times x, is the same as the limit as n approaches infinity, n plus 1 times the absolute value of x. Now, if x is non-zero, then you know that absolute value of x is going to be positive. N plus 1 is growing without bound, which means n plus 1 times the absolute value of x is going to grow without bound if x is non-zero. So the only way we're going to get a finite limit here is if x is equal to 0, and in that case, that limit would just be 0. But it's certainly worth mentioning this limit is going to be infinity when x is not equal to 0. And this limit is 0 when x is equal to 0. Because think about what happens. If x is equal to 0, n plus 1 times 0 is just going to give us 0. Limit as n approaches infinity of 0 is 0. So we know that in the case where x is equal to 0, the limit we get from this ratio test is less than 1, which means we'll have convergence when x is equal to 0, and we'll have divergence for every other real x value. So what this tells us is that series only converges if x is equal to 0. Sometimes it happens that way. Sometimes your given power series will only converge at a single x value. But it's not always that way. So let's take a look at the next example. And so for this example, we're going to figure out for which values of x does our series converge. And so this time we're going to have the summation n equals 1 to infinity. X minus 3 raised to the n divided by n. So for which values of x does that series converge? Now, in order to answer this question, once again, we're going to use the ratio test. And if we're going to use the ratio test, then we need to know something about a sub n and a sub n plus 1. Now, a sub n is just our general term here. We have x minus 3 raised to the n power over n. And a sub n plus 1 is x minus 3 raised to the n plus 1 divided by n plus 1. So if we're going to use the ratio test, then yet again we need to consider this limit. Well, the limit as n approaches infinity. Absolute value of a sub n plus 1 over a sub n. Now, we're going to need to plug in what we know about a sub n plus 1 and a sub n. So we have the limit as n approaches infinity, x minus 3 raised to the n plus 1 over n plus 1 divided by x minus 3 to the n over n. Well, remember that dividing by this is the same as multiplying by its reciprocal. So we're going to have the limit as n approaches infinity. Oh, and this should be absolute value. Yeah, don't forget the absolute values like I just did. So should have the absolute values there. And we'll have the absolute value of, we'll have x minus 3 raised to the n plus 1 over n plus 1. And that'll be times n over x minus 3 raised to the n. Now, if you think about n and n plus 1, well, n is growing without bounds, so both n and n plus 1 are going to be positive here. So what this is going to end up giving us, limit as n goes to infinity of n over n plus 1 times absolute value of x minus 3. Because notice we have x minus 3 raised to the n plus 1 power up top, x minus 3 raised to the n power on the bottom. Divide like basis, subtract the exponents. N plus 1 minus n gives us 1, so we'll have this limit here. But keep in mind that as n grows without bound, n over n plus 1 is tending toward 1. So this limit is actually going to be the absolute value of x minus 3. Now, let's keep in mind what the ratio test actually tells us. Well, what the ratio test tells us is that if this limit is less than 1, then we have a convergent series. If this limit is finite and greater than 1, or if it's infinity, we have a divergent series. And if the limit is equal to 1, then the test is inconclusive. So one thing we know is that, for sure, this series is going to converge if the absolute value of x minus 3 is less than 1, because after all, absolute value of x minus 3 is our limit here. But for sure, we know that the series converges if the absolute value of x minus 3 is less than 1. Now, if you think about what that actually means, it means that if we have plus or minus x minus 3 is less than 1, then we're going to have x is less than 4 from this part. Here we'll have negative x plus 3 is less than 1, which means negative x is less than negative 2, or x is greater than 2. So we know that if x is between 2 and 4, then we have convergence. So the series converges. If x is between 2 and 4. Now, that doesn't necessarily tell us the entire story. See, what you have to keep in mind is that if x is equal to 2, for example, absolute value of 2 minus 3, absolute value of negative 1 is 1, which means the ratio test is inconclusive. And if x is equal to 4, absolute value of 4 minus 3 is 1. Once again, ratio test is inconclusive. So what we're going to need to do to figure out if we have convergence at 2 and at 4 is we're going to have to test the series at those particular x values. So we're going to let x equal 2 and see what happens. Now if we let x equal 2, we go back to our original series and we plug in 2 for x. So we're going to get summation n equals 1 to infinity of 2 minus 3 raised to the nth power divided by n. But remember, 2 minus 3, yeah, that's negative 1. So we'll have the summation n equals 1 to infinity, negative 1 to the n divided by n. Now this series is your alternating harmonic series, and we saw several sections ago, this series actually converges. So we know that this series is actually going to converge when x is equal to 2. But we're going to have to test this other endpoint of this interval. So let's let x equal 4, and we'll see what happens there. Well, if x equals 4, we go back to this series plugging in 4 for x. And what we're going to get is summation n equals 1 to infinity, 4 minus 3 raised to the nth power divided by n. So remember, the 4 minus 3 gives us 1. 1 to the n gives us 1. And so we'll have summation n equals 1 to infinity, 1 over n. This is our harmonic series, which we know diverges. And so based on this analysis, what we know is that power series converges. For x greater than or equal to 2 and strictly less than 4. Right. Let's take a look at another example. So at this point, we have an example where the series converges for a single x value. Here we have an example of a series that converges over this interval, half open interval from 2 to 4. But let's take a look at another example. And so for this example, we're going to find the domain of the Bessel function of order 0. And the way we define this j sub 0 of x, summation n equals 0 to infinity. And our general term is negative 1 to the n times x to the 2n over 2 to the 2n times the square of n factorial. Right, so that's our function, and we're going to try to figure out where this power series converges. Well, once again, we're going to use the ratio test. If we're going to use the ratio test yet again, we need to know what's going on with a sub n as well as a sub n plus 1. So our a sub n, we have negative 1 to the n times x to the 2n over 2 to the 2n times the square of n factorial. If you take a look at a sub n plus 1, we're going to have negative 1 raised to the n plus 1 times x to the 2n plus 2, it turns out, because if I replace the n here with n plus 1, remember 2 times n plus 1, 2n plus 2. So we'll have x to the 2n plus 2. And then here, replace the n with n plus 1, we'll have a 2 raised to the 2n plus 2. And then we'll have an n plus 1 factorial squared. Now, once again, we have to investigate this limit. And so we'll have the limit as n approaches infinity of the absolute value of this over that. So, absolute value of this thing. So this is going to be the same as the limit n approaches infinity. Now remember, dividing by this thing is equivalent to multiplying by its reciprocal. So the limit as n approaches infinity of the absolute value of our negative 1 to the n plus 1 times x to the 2n plus 2 over 2 to the 2n plus 2 times the square of n plus 1 factorial, and then times 2 to the 2n times the square of n factorial over negative 1 to the n times x to the 2n. Now let's keep in mind there's quite a lot going on here, but there's a tremendous amount that we can do to simplify this going forward. So I'll have the limit that approaches infinity. Now let's think about the negative 1 to the n plus 1 over the negative 1 to the n. That's going to give us a negative 1 up top. Let's take a look at our x to the 2n plus 2 up top, x to the 2n on the bottom. Divide like basis, subtract the exponents. 2n plus 2 minus 2n gives us 2. So we'll have an x squared up top. Two to the 2n up top, 2 to the 2n plus 2 on the bottom. So we'll get a 2 squared or a 4 downstairs. And then we'll have the n factorial squared over the square of n plus 1 factorial. Now if we think about that sort of separately, we'll have n factorial squared over the square of n plus 1 factorial. Now this is going to be the same as n factorial times n factorial over n plus 1 factorial times n plus 1 factorial. But remember the observation from not too long ago. It's an observation we've looked at several times in this chapter. And that is that n plus 1 factorial is the same as n factorial times n plus 1. And so each of these is going to give us an n factorial times n plus 1. Now, the n factorials on the bottom will reduce out with the n factorials up top, and what we'll be left with is a 1 over the square of n plus 1. And so, with that being said, the n factorial squared over the n plus 1 factorial squared is a 1 over the square of n plus 1. So we'll have an n plus 1 raised to the second power downstairs with the 4. Now, this is going to give us limit as n approaches infinity of 1 over 4 times n plus 1 squared times x squared. But as n approaches infinity, this 1 over 4 times the square of n plus 1 is tending towards 0. So that means this limit is going to be 0, just less than 1. And it's not going to matter what x is. X could be any real number you want it to be. The limit's still going to work out the same way. And so what that means is that this series converges for all real numbers. All right, so the domain set of all real numbers. So, taking a look at the previous 3 examples. First example, we had convergence at a single x value. Second example, we had convergence over this half-open interval from 2 to 4. Most recent example, we have convergence over the entire set of real numbers. And it leads us to the following theorem. And so what this theorem tells us is that for a given power series, general term c sub n is x minus a raised to the nth power, we have 3 possibilities. Possibility number 1, the series converges only when x equals a. That's the situation that we saw in the very first example. Second possibility, the series converges for all x. That's the example we saw most recently. And the third possibility is that there is a positive number r such that the series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. That was the situation we found ourselves in the second example. And one thing to keep in mind is that if the absolute value of x minus a is equal to r, then you're going to need to test those x values in the given series to figure out whether you have convergence or divergence. Now, this leads us to the following definition. This number r is called the radius of convergence of the power series. And so in the situation where, second example, where we had x greater than or equal to 2, strictly less than 4, radius of convergence in that case is 1. The series was centered at 3, so yeah, this was, the radius of convergence in that case was 1. Now, by convention, if we take a look at this case where the series converges only when x is equal to a, we say the radius of convergence in that case is 0. And in case 2, where the series converges for all real x, then we say that the radius of convergence is infinity. So we say that r is equal to 0 in case 1. This is case 1 of the theorem. R equals infinity in case 2. That's case 2 of the theorem. Now, as we go along with that, we have something called the interval of convergence. So the interval of convergence of power series is the interval that consists of all x values for which the series converges. So let's take a look at an example. So here we're going to find the radius of convergence and interval of convergence. Of the series. Here we're going to have the summation n equals 0 to infinity. Negative 3 raised to the n power times x to the n over the square root of n plus 1. Now, we're going to need to, once again, use our ratio test to help us figure this out. And of course, using the ratio test, we need to know about a sub n and a sub n plus 1. So we'll go ahead and write those down. So a sub n plus 1 will have negative 3, replace the n here with n plus 1, times x to the, and once again replace the n here with n plus 1. So negative 3 to the n plus 1, times x to the n plus 1. And then on the bottom, if we replace the n here with n plus 1, n plus 1 plus 1, which means n plus 2 is underneath the radical. Alright, so let's take a look. The limit that approaches infinity. Absolute value of a sub n plus 1 over a sub n. So here we're going to get the limit that approaches infinity of negative 3 raised to the n plus 1 times x to the n plus 1 over the square root of n plus 2. Put that over negative 3 raised to the n times x to the n over the square root of n plus 1. And then remember, dividing by this is the same as multiplying by its reciprocal. And in fact, if you really wanted to, you could go directly from here to the step I'm about to write. All right, so we're going to need to simplify this a bit. And one of the things to keep in mind is that you have a negative 3 raised to the n plus 1 here, a negative 3 raised to the n on the bottom. So that's going to give us a negative 3 up top. And then we'll have x to the n plus 1 up top, x to the n on the bottom, leaves us with x up top. And then we'll have square root of n plus 1 up top, square root of n plus 2 on the bottom. But this would be the same thing as the limit that approaches infinity of the square root n plus 1 over n plus 2 times the absolute value of negative 3x but as n gets larger and larger, this part's getting closer and closer to 1. So we're going to get a limit. It's actually the absolute value of 3x, or we could write it as 3 times the absolute value of x. So that's going to be our limit, 3 times the absolute value of x. Now, in order to guarantee convergence using the ratio test, we're going to need this limit to be less than 1. So we know the series converges. we know the series converges if 3 times the absolute value of x is less than 1. And we know it diverges if 3 times the absolute value of x is greater than 1. So, series converges if the absolute value of x is less than a third. Okay, so if you divide both sides by 3, the absolute value of x less than a third, or if x is strictly between negative 1/3 and positive 1/3, we know we have convergence. What this doesn't tell us is what happens at the 2 endpoints. Because remember, if x is negative 1/3, or if x is positive 1/3, this limit's going to be 1, and the ratio test is inconclusive in both of those situations. So what it means is that we're going to need to test what happens when x is negative 1/3, and test what happens when x is positive 1/3, going back to this original series. So we'll start, we'll let x equal negative 1/3. Okay. So we'll have summation n equals 0 to infinity, negative 3 to the n, there's a negative 1/3 to the n, over the square root of n plus 1. But if you think about what this actually means, you take negative 3 to the n, that's negative 1 to the n times 3 to the n. Negative 1/3 to the n is a negative 1 to the n times a third to the n. I take negative 1 to the n times negative 1 to the n, that gives me negative 1 to the 2n. Well, negative 1 raised to an even power is always going to give me 1. 3 to the n times 1/3 to the n, it's going to give me 1 to the n. So it turns out this numerator in that general term is just 1. So we'll have summation n equals 0 to infinity of 1 over the square root of n plus 1. Compare this series to the series of general term 1 over the square root of n. That would be a divergent p-series, and what you'll find is that this series is in fact divergent. So we know that we're going to pull strict inequality here. If x is equal to negative 1/3, we know that the series here doesn't converge, it diverges. What we don't know just yet is what happens if x is equal to positive 1/3, so we need to test that. And so if we take a look at what happens when x is a third, we'll have a summation n equals 0 to infinity, negative 3 to the n times 1/3 to the n over the square root of n plus 1. And if you take a look at this numerator, that's going to break down into negative 1 to the n times 3 to the n times 1/3 to the n. But your 3 to the n times 1/3 to the n will give you 1 to the n, or 1, which means the top part just reduces down to this negative 1 raised to the nth power. So we'll have summation n equals 0 to infinity, negative 1 to the n over the square root of n plus 1. Now, if you take a look at that series, one thing you might notice, it is an alternating series. So if you take a look at b sub n, that's going to be 1 over the square root of n plus 1. We know b sub n plus 1 will be 1 over the square root of n plus 2, and leads us to 2 observations. Number 1, b sub n plus 1 is less than or equal to b sub n for n greater than or equal to 0. And the limit as n approaches infinity of b sub n, limit as n approaches infinity of this thing is 0. So both conditions of the alternating series test are satisfied, which means this is a convergent alternating series. Well, when x is negative 1/3, we have divergence. X is positive 1/3, we have convergence. So our interval of convergence negative 1/3 is our left boundary, but we don't include it. Positive 1/3 is our right boundary, and we do. Series is centered at 0, and if you take a look at the distance from the center of the interval to one of the endpoints, you'll notice that distance is 1/3. So the radius of convergence in this case is r equals 1/3. Of course, we could have answered that a while ago, but so there we have it. I think I would like to take a look at one more example before we call this section finished. So here we're going to find the radius of convergence and the interval of convergence of the series. And this time we'll have the summation n equals 0 to infinity. And we'll have an n times x plus 2 raised to the nth power divided by 3 to the n plus 1. Now, I know this may come as a big shock, but we're going to use the ratio test. And again, just like all the other examples we've looked at so far, we're going to need to know something about a sub n and a sub n plus 1. So our a sub n is n times x plus 2 raised to the n over 3 to the n plus 1. And our a sub n plus 1 is going to be n plus 1 times x plus 2 to the n plus 1 over 3 to the n plus 2. Now we need to know something about this limit. And so we'll have the limit as n approaches infinity. The n plus 1 times x plus 2 raised to the n plus 1 over 3 to the n plus 2 over n times x plus 2 to the n over 3 to the n plus 1. Of course, we're taking the absolute value of that. And just like before, dividing by this is equivalent to multiplying by its reciprocal. So we'll have the limit n approaches infinity n plus 1 times x plus 2 to the n plus 1 over 3 to the n plus 2 times, and then flip this, we'll have 3 to the n plus 1 or n times x plus 2 to the n. And there will be quite a bit of simplification. So, for example, you may notice there's an n plus 1 here and an n here. So let's go ahead and write the limit as n approaches infinity. And I can keep the n plus 1 over n outside the absolute value signs because as n gets larger and larger, we know this is going to be positive anyway. But then we'll have x plus 2 to the n plus 1 over x plus 2 to the n. That'll leave us with an x plus 2 up top. And then we have a 3 to the n plus 1 over a 3 to the n plus 2. We have one extra factor of 3 here. So it's going to stay on the bottom. Well, we know that as n gets arbitrarily large, the n plus 1 over n is tending toward 1. So really what this limit, it turns out to be, is 1/3 the absolute value of x plus 2. And as long as that limit is less than 1, we're guaranteed convergence of this power series. So power series converges if 1/3 times absolute value of x plus 2 is less than 1, or multiply both sides of that inequality by 3, the absolute value of x plus 2 is less than 3. Now if you think about that as it pertains to endpoints of an interval, we know that if we had an equal sign here, if x is equal to 1, that would work. And also if x equals -5, that would work. So the endpoints of our interval will be -5 and +1. So power series converges if x is between -5 and +1. You can also just directly solve your absolute value inequality here, much the same way I did in one of the previous examples. What we don't know at this point, however, is what happens when x is -5, or what happens when x is 1. Because if x is -5, for example, then our limit is 1/3 times absolute value of -3. It's 1/3 times 3, which is 1. Ratio test is inconclusive. And if x is 1, same story. 1 plus 2 gives us 3. 1/3 times 3 gives us 1. So yeah, ratio test is inconclusive yet again. So what we're going to need to do is figure out what happens when x is equal to -5. And then later on we'll figure out what happens when x is 1. So let's think about plugging in -5 for x. So we'll have summation n equals 0 to infinity, n times -5 plus 2 raised to the n over 3 to the n plus 1. Now that's going to give us summation n equals 0 to infinity, n times -3 to the n over 3 to the n plus 1. If you think about it, -3 raised to the n can be written a little differently. We can write it as -1 to the n times 3 to the n. And if we do that, then we can reduce this a bit because you have 3 to the n up top, 3 to the n plus 1 on the bottom. That gives us a factor of 3 downstairs. And so what you'd have is summation n equals 0 to infinity, of negative 1 to the n times n divided by 3. Now, if you take a close look at this, you notice that we get a divergent series here, because as n grows larger and larger, negative 1 to the n times n over 3 is going to grow without bound in absolute value. So these terms definitely aren't tending towards 0 as n approaches infinity. So this is going to diverge by the test for divergence. Now we're also going to need to figure out what happens when x is equal to 1. So if x is equal to 1, once again, go back to your original series. We'll have the summation n equals 0 to infinity. N times 1 plus 2 raised to the n over 3 to the n plus 1. But your 1 plus 2 raised to the n is 3 to the n. So up top you'll have n times 3 to the n. On the bottom you have your 3 to the n plus 1. But your 3 to the n over 3 to the n plus 1 is a third, which means your general term is going to be n over 3. And I think it's safe to say that we have a divergent series here, considering the fact that the limit as n approaches infinity of n over 3 is definitely not 0. So this series is going to diverge. So we have divergence at the two endpoints, which means that the interval convergence is open interval from -5 to 1, and the radius of convergence is r equals 3. Now, keep in mind that from the beginning we know this is a power series centered at -2. So -2 is notice it's the center of this interval, and the distance from the center to either of the endpoints is 3 units. So radius convergence is r equals 3 in this case. And with that, section 11.8 is finished. So I have several recommended exercises I would like for you to take a look at. We have 3, 7, 9, 13, 15, 19, 23, and 27.